Shh. We are now going to go over problems 1 through 5 on the worksheet that I gave you. You had to use the water heating curve to be able to answer most of the questions. When we look at question number 1, it's just defining what latent heat is. Latent heat is the amount of energy needed to change states of matter. We wrote this actually on our reference sheet. There we go. So it's the amount of heat exchanged between solid and liquid, liquid and solid, or between liquid and gas and liquid. So that's your answer for number 1. Number 2, why does the temperature of water not increase when it's boiling? Well, look at the graph. As we add heat, it's boiling right here when it's going between liquid and gas. The temperature is not going up because what's happening is you're going from weak intermolecular forces to no intermolecular forces. That change going from weak to no intermolecular forces, all this heat, this, which is delta H vap, is going towards changing the state of matter. We showed this with the jiggy molecule example. All the heat I'm adding, the temperature won't go up, it's going into changing the state of matter. So once you get to that phase change, all the heat you add is going towards breaking those intermolecular forces. The next question is on, let me make sure I have this up. Next question, number 3, describe the difference between latent heat of fusion and latent heat of vaporization. Latent heat of fusion, you should have said, is for going between solids and liquids. For latent heat of vaporization is between liquid and gas. Which process involves energy being absorbed? Now that's kind of a trick question because both do. If you are going from a solid to a liquid, you need to absorb energy. If you're going from a liquid to a gas, you need to absorb energy. So if it's latent heat of fusion, liquid to solid to liquid, that's absorbing. Liquid to gas, with latent heat of vaporization, that's absorbing. Number 4, water condenses on the outside of a soda can. So this is question number 4A. On 4A, is energy being released or absorbed? Well, let's think about the change that's happening. You're going from a gas to a liquid, that's condensation. Now, always refer back to the graph that we have. The graph that we have shows how water changes. Goes up, flat, goes up, flat, goes up. This is the gas, this is the liquid. If you are going from a gas to a liquid, you're going downhill on this graph. What that means is energy is being released. If you go uphill on this graph, energy has to be absorbed by your sample. So in this case, for this problem, since you're going from a gas to a liquid, from there to there, energy is released. That's why when you have a cold soda can, you're essentially going from you're cooling down the gas molecules and you're going into the liquid state of matter. B, what phase change is water going through? What you would say for 4B is you would say vaporization. Specifically, you could have written delta H vap. 4C, if you wanted to calculate the heat transfer, what formula would you use? So we go here. We're using the latent heat of vaporization because we're going from a gas to a liquid. So the formula you would use is Q equals M delta H vap. Class, do we have any questions about the answers I've put for number 4? Number 5. On number 5, it's saying that calculate the energy transferred when 4.6 grams. Let's write this out with a given, a formula, and then work, which I showed you guys earlier. So the given information in this problem is they tell us it's 4.6 grams of ice. Now, ice is water, which is H2O, in the solid state of matter. Then it says it's at 0 degrees Celsius, 0.0 degrees Celsius. And the change that's happening is we're taking that solid ice and we're melting it, so it's going to go to H2O liquid. Class, do we have any questions about that? All right, so now let's go to our formula sheet. On our formula sheet, let's remind us that the fusion number, this is for going between solid and liquid. Latent heat of vaporization is between liquid and gas. Since I'm melting ice, I'm going from solid to liquid. So the formula I'm going to use is the latent heat of fusion. So my formula for problem 5 is Q equals M delta H sub fuse. All right, so now let me go ahead and plug in my numbers. So Q equals the mass, which is 4.6 grams, times the delta H fuse. Well, what is delta H fuse for ice? this is where we go to the constants on our formula sheet. These two stars down here. Specifically, put a box around this because we deal with all of our numbers with joules, not calories. So we're looking for delta H fuse, which is this one right here for water. It's different for other substances. So the delta H fuse for water is 334 joules per gram. So I put 334 joules per gram. This delta H fuse, therefore, is a constant, meaning it's something you look up. It's a value that's been measured by chemists in previous times, and it will always be 334 joules per gram for water. Now, if it's a different substance, it'll be a different number. Class, do we have any questions about that? Do you need me to show how the grams cancel out and what the answer is, or are we good to go? We get it's just two numbers we're multiplying. All right, now I'm going to show you a problem that's a lot more difficult. It's going to be problem number 2 from the back side on your worksheet. So go to the back of the worksheet, go to number 2, and what we're going to do is do number 2 together as a class. And keep this handy. The water heating curve is going to help us out quite a bit. So I'm jumping way ahead to a harder problem, and please ask questions as we move along. So in this problem, for number 2, we are going to write out all the given information. So when I look at the question, you want to write down everything that's a number. The 29.5, the 14, the 0, and the 0, okay? So let's go ahead and just start transcribing what's in the question. 29.5 grams. It said it's liquid water. Since it's liquid water, I'm just going to write H2OL. And then it decreases from 14 degrees Celsius to 0.0 degrees Celsius. So it's going down in temperature. That means that I started at a higher temperature, and then I went down to a lower temperature. So this is my initial temperature. This is the temperature I dropped it to. This is in grams, so I know that's mass. 0 degrees Celsius I'm not going to write out again because it's redundant. Now on the formula for this problem, we're going to get in the practice of literally drawing out the water heating curve. So go ahead and draw out the water heating curve really quickly. And remember, goes up, goes flat, goes up, goes flat, goes up again. Solid, liquid, gas. This is our melting and our freezing. This is our boiling and our condensing. So in this question, let's draw out what's happened. What's happening is we're starting at 14 degrees Celsius. Well, remember, it goes flat right when you have that melting and you have that freezing, and that's at 0 degrees Celsius. And then up here, this is at 100 degrees Celsius. And don't forget, this is H, enthalpy on the bottom. Over here, it's temperature. Okay, so I'm going to put a circle where I started at in this question. The question says I start at 14 and I go down to 0. So I go from here down to there. Any questions about that? And then it says it freezes it. So then I go from there to there. Well, we just learned in the last question that if I'm melting or freezing something, I'm using delta H fuse. But I have this additional change that has to happen. Before I can freeze it, I have to lower its temperature. There's only one equation from causing it for a temperature change. I'm going to actually get out a new reference sheet that's a little bit cleaner. It's going to be this one right here. In all of these problems, there are only 3 equations for calorimetry. Only 3. That's it. There's only one of them that involves a temperature change. So the first part of this problem, I'm going to have to use this equation because I'm going from 14 to 0. So the very first equation is going to be Q equals MC delta T. Now I know on your formula sheet it's written out different. On your formula sheet it's written out as Q equals M delta T Cp. Trust me, it's the same thing as what I taught you before. Then the second change that occurs, I go from the liquid to now at 0 and not changing temperature, 0 to 0. Doesn't change temperature, but it does change states of matter. So now I look and I'm like, which one is liquid to solid? Liquid to solid. Not vape. Vape sounds like gas. It's got to be this one. So I'm going to use this as my second equation in the problem. So it's Q equals M delta H fuse. Okay, so this problem has two formulas. The first formula is for the first change, which is the temperature change, Q equals mc delta T. The second formula is for the second change, where it's the phase change, Q equals m delta H sub fuse. Now, work. We're going to write out the work for the problem. Let's do the first equation first. So Q equals, and let's call this Q1 because this is the first change. Q1, the mass is 29.5 grams. What's the specific heat of water? Well, I know the specific heat of water is 4.18 joules per gram degree Celsius. What's the temperature change? Well, it goes from 14 to 0, but remember, delta T, this value right here is always TF minus TI, so it's 0 minus 14, which means it's negative 14 degrees Celsius. So I'm going to take my calculator, and I'm going to plug in those three numbers. So I've got 29.5 times 4.18 times negative 14, and then I get Q1 equal to negative 1,726.34 joules. Now, in all of these problems, we have only two sig figs. So if you're rounding it to significant figures, just wait until the very end of the problem to round it to significant figures. So that's the first change. I've calculated it successfully for the very first change. Now I'm going to do it for the second change, Q2. Now I'm using this equation. So the next equation is Q equals the mass, which is 29.5 grams. I don't know why I wrote that out. That's redundant. It's the same thing. Times the delta H fuse, which I'm going to look that up. Where's delta H fuse? There it is. There's the number, 334 joules per gram. So go ahead and plug that in to get your Q2. 29.5 times 334. You get 98.53 joules. Okay. Now, that doesn't tell us how much energy total it took to drop the water from 14, how much energy was released when it went from 14 to 0 and from 0 to 0 when it froze. The whole time it's going downhill, so it's releasing energy, which makes sense. You don't put water on a stove to freeze it. You want to take energy away from it by putting it in a lower temperature environment. So if I want to figure out my total Q, the total amount of energy, what I'm going to have to do is add my Q1 and my Q2. But this is where it actually is the only tricky part of this problem. I say only, there are other parts that can be confusing, but the most confusing part is these numbers. See how this one came out to be negative? See how this one came out to be positive? Well, we know that this Q2 was when it was freezing, right? If something's freezing, what that means is it's losing that energy, not absorbing that energy. So if energy is being released, you have to make it negative, even though the equation gives you a positive number. So I'm going to add these two values, but they're both negative. So negative 1726.34 joules plus negative 9,853 joules. So your total amount of energy, and I'm going to round this to the correct number of significant figures, is, let me do 1726.34 plus, what is it, 9,853 is negative and 11,579.34 joules. But we want to round this to the correct number of significant figures, which for you guys would be, actually, believe it or not, only negative 12,000. Class, are there any questions about how I did any of the steps in this problem? That is the hardest it gets. I jumped to the hardest one first. A lot of the other ones are easier. There's only one equation you need to use. No other questions? All right.